We may have already found alien life and just don't know it yet. Right now, orbiting Saturn, there's a moon shooting samples of a hidden ocean directly into space. Every second, 200 kilograms of water vapor, ice particles, and organic molecules erupt from beneath its frozen surface. Scientists have analyzed these samples and found something extraordinary. All the essential ingredients for life exist in that alien ocean, in conditions that mirror the environments where life first emerged on Earth. This isn't speculation based on faint signals or distant observations. We've flown through those plumes, collected the material, and studied its chemistry in detail. What we discovered has fundamentally changed how we think about life in the universe. Enceladus measures just 500 kilometers in diameter, roughly the distance from New York to Detroit. You could fit it comfortably inside the borders of France. At -198 degrees Celsius, its surface ranks among the coldest places in our solar system. The moon reflects nearly all sunlight that touches it, appearing as a brilliant white sphere against the darkness of space. For more than 2 centuries after William Herschel spotted it through his telescope in 1789, Enceladus seemed unremarkable, just another frozen world in Saturn's collection of over 80 moons. Then in 2005, everything changed. NASA's Cassini spacecraft approached the moon for a routine flyby, expecting to photograph another dead, cratered surface. Instead, the cameras captured something no one anticipated. The South Polar region showed almost no impact craters, despite billions of years of bombardment that scarred every other object in the solar system. The terrain looked impossibly young, carved by geological forces that should have died long ago on such a small world. Cassini's instruments began detecting anomalies. Temperature readings showed the South Pole radiating far more heat than solar radiation could explain. Then the spacecraft's magnetometer picked up disturbances in Saturn's magnetic field near Enceladus, signatures that suggested charged particles, possibly water vapor, escaping the moon's gravitational pull. Mission controllers adjusted Cassini's trajectory for a closer look. What the spacecraft revealed defied conventional planetary science. Enormous plumes of water vapor and ice crystals erupted from 4 massive fractures in the southern ice shell, features scientists would later name tiger stripes for their distinctive parallel pattern. These weren't small geysers. The plumes reached hundreds of kilometers into space, powerful enough to supply most of the material forming Saturn's diffuse E-ring. The discovery answered an old mystery. Astronomers had long wondered why Saturn's E-ring existed at all. Orbital mechanics dictate that such rings should dissipate over time unless something continuously replenishes them. Enceladus was that source, constantly feeding the ring with fresh ice particles ejected from its interior. But discovering active geology on a moon this small raised more questions than it answered. Worlds the size of Enceladus should have frozen solid billions of years ago, their internal heat long since radiated into space. Yet here was a tiny moon exhibiting volcanic activity, though instead of molten rock, it erupted with water and ice. Scientists call this cryovolcanism, and Enceladus displayed the most dramatic examples ever observed. The heat source became the central puzzle. Cassini's instruments measured the thermal output from the tiger stripes and found them emitting roughly 15 gigawatts of power, equivalent to 20 large power plants operating continuously. This energy had to come from somewhere, and the only viable explanation involved tidal forces. As Enceladus orbits Saturn, the giant planet's immense gravity pulls and squeezes the moon's interior. This constant flexing generates friction, converting mechanical energy into heat through a process called tidal heating. Other moons experience tidal heating. Jupiter's Io has so much that it's the most volcanically active body in the solar system, constantly resurfacing itself with molten sulfur and silicate lava. But Enceladus presented a different scenario. The heat wasn't melting rock but maintaining liquid water beneath an ice shell, creating an environment vastly more interesting to astrobiologists. Mission scientists quickly realized the Plumes offered an unprecedented opportunity. Unlike Europa, Jupiter's moon suspected of harboring a subsurface ocean beneath kilometers of solid ice, Enceladus was bringing samples of its ocean directly to the surface and launching them into space. No need for complex drilling missions or melting through ice shells. Cassini could simply fly through the Plumes and collect material for analysis. The spacecraft executed multiple daring flybys, some passing within 25 kilometers of the surface, threading between the towering ice geysers. Each pass provided new data about the plume composition, building a chemical profile of the hidden ocean below. The ion and neutral mass spectrometer detected water vapor comprising roughly 98% of the plume material. The remaining 2% contained a mixture of other compounds that would prove far more significant than their small percentage suggested. Scientists found molecular nitrogen, carbon dioxide, methane, and traces of ammonia. Simple hydrocarbons appeared in the data, including propane and acetylene. These weren't just random chemicals. Their presence indicated active chemistry occurring somewhere beneath the ice, processes that required energy and specific conditions to produce these molecules. Then Cassini detected something that transformed Enceladus from a geological curiosity into one of the most important targets in astrobiology. Embedded in the ice grains were organic compounds, carbon-based molecules including benzene and complex macromolecular structures containing at least 15 carbon atoms. Some of these organics reached 200 atomic mass units, large enough to qualify as the building blocks of biochemistry. The discovery of organics alone would have been significant. But the mission found something even more compelling in 2017 during one of Cassini's final flybys. The mass spectrometer detected molecular hydrogen streaming from the plumes in substantial quantities. This wasn't a trace detection but a clear, unambiguous signal. Hydrogen in this context meant only one thing. Somewhere on Enceladus's ocean floor, hot water was reacting with rock in a process called serpentinization. On Earth, this same reaction occurs at hydrothermal vents on the ocean floor, where seawater seeps into cracks in the crust, gets heated by volcanic activity, and reacts with minerals in the rock. The process strips hydrogen from water molecules and releases it as free molecular hydrogen gas. Finding hydrogen was like discovering a smoking gun. It meant Enceladus wasn't just harboring a static ocean of cold salt water. The moon had an active seafloor where geological and chemical processes were continuously operating, creating chemical energy that life could potentially exploit. On Earth, entire ecosystems thrive around hydrothermal vents in complete darkness, thousands of meters below the ocean's surface where sunlight never penetrates. These communities don't rely on photosynthesis. Instead, specialized microorganisms harvest chemical energy from the minerals and gases dissolved in the hot vent fluids. They convert hydrogen and carbon dioxide into organic molecules through a process called chemosynthesis, forming the base of a food chain that supports larger organisms like tube worms, crabs, and fish. The chemistry Cassini detected in Enceladus's plumes matched the chemistry of these vent environments remarkably well. The moon appeared to have everything necessary to support similar ecosystems, assuming life could arise in such conditions or had somehow been delivered there in the distant past. Cassini continued its reconnaissance missions, gathering more data with each flyby. Scientists began distinguishing between different types of material in the plumes. Some ice grains appeared fresh, having been ejected just minutes before Cassini sampled them. Others showed signs of aging, their surfaces modified by exposure to Saturn's intense radiation environment during their time in the E-ring. The fresh grains proved more valuable for understanding ocean chemistry. Radiation can create organic molecules on ice surfaces through purely chemical processes, potentially confusing the picture of what's actually happening in the ocean versus what forms in space. By focusing on recently ejected material, researchers could be more confident they were analyzing genuine ocean samples rather than radiation-generated artifacts. Analysis of these fresh grains revealed even more complex organic chemistry than earlier observations suggested. In 2026, scientists announced the discovery of additional compound classes in archived Cassini data, including aliphatic esters, heterocyclic molecules, and nitrogen-bearing organic compounds. The variety of organics kept expanding as researchers developed new techniques for extracting information from the mission data. Each discovery added another piece to a remarkable puzzle. Enceladus wasn't just geologically active. It hosted a chemically rich ocean containing the fundamental ingredients that, on Earth, living organisms use to build cells, store genetic information, and harvest energy from their environment. But having the right ingredients doesn't automatically mean life exists. You can stock a kitchen with flour, eggs, sugar, and butter without producing a cake. The components need to come together under the right conditions, following specific processes that transform raw materials into something organized and functional. The question scientists now faced was whether Enceladus provided not just the ingredients but also the recipe. And answering that question would require understanding exactly what conditions exist in that hidden ocean and whether those conditions could support the chemical reactions necessary for life to emerge and persist. The ocean beneath Enceladus is not a simple body of water. Chemical models reconstructing the conditions down there suggest an environment far stranger than Earth's familiar seas. The pH hovers somewhere between 7.95 and 9.05, making it moderately alkaline rather than neutral like pure water. That might sound like a minor detail, but pH fundamentally shapes which chemical reactions can occur and how efficiently they proceed. Think about your stomach acid. It's highly acidic, with a pH around 2, specifically because that acidity helps break down food and kill bacteria. Change that pH significantly and the entire digestive system fails. Ocean chemistry works similarly. The alkalinity of Enceladus's ocean creates specific conditions that favor certain types of chemical processes while inhibiting others. What makes this particularly interesting is the comparison to environments on Earth where life thrives in alkaline conditions. Soda lakes scattered across Africa, Asia, and North America have pH levels between 9 and 11. They're harsh environments by most standards, with water chemistry that would burn human skin, yet they teem with specialized microorganisms that have adapted to exploit these exact conditions. Enceladus's ocean chemistry resembles these terrestrial soda lakes more closely than it resembles normal seawater. The salt content tells another story. When Cassini analyzed ice grains from the Plumes, it detected sodium chloride, ordinary table salt, the same compound that makes Earth's oceans salty. But the grains also contain significant amounts of sodium carbonate, a compound less common in terrestrial seawater but abundant in soda lakes. This specific combination provides clues about what's happening at the ocean floor. For sodium carbonate to form and remain stable in solution, the ocean water must be interacting with specific types of rock under particular temperature and pressure conditions. Laboratory experiments recreating these interactions show that when water at the right temperature flows through rock containing certain minerals, it dissolves some compounds while precipitating others, gradually shifting the water's chemistry toward the alkaline, carbonate-rich state observed at Enceladus. But here's where it gets really compelling. In 2023, scientists announced the discovery of phosphorus in the plume material. Phosphorus had been the missing ingredient, the one element from the CHNOPS list that hadn't been definitively detected. Carbon, hydrogen, nitrogen, oxygen, and sulfur were already confirmed. Phosphorus was the gap. Why does phosphorus matter so much? On Earth, every living cell uses phosphorus in absolutely critical ways. Your DNA's backbone is built from alternating sugar and phosphate groups. The molecule that stores and transfers energy in cells, ATP, contains 3 phosphate groups. Cell membranes incorporate phosphorus-containing lipids. Remove phosphorus and biochemistry as we know it simply stops functioning. The concentration levels were the real surprise. Models based on the detection suggested Enceladus's ocean contains phosphorus at concentrations at least 100 times higher than Earth's oceans. Some estimates push that to several hundred times higher. This abundance isn't just adequate for life, it's generous, eliminating what could have been a significant bottleneck for any biochemistry attempting to get started. Where does all this phosphorus come from? The answer appears to lie in those same water-rock interactions happening at the ocean floor. Certain minerals in rocky material contain phosphorus locked in their crystal structures. Under the right conditions, when hot alkaline water flows past these minerals, it can dissolve phosphorus-containing compounds and carry them into the ocean as dissolved phosphates. Laboratory simulations have demonstrated this process. Researchers created artificial Enceladus ocean water, mixed it with powdered rock samples similar to what might exist in the Moon's interior, heated the mixture to temperatures matching those expected near hydrothermal vents, and pressurized it to simulate deep ocean conditions. When they analyzed the water afterward, phosphorus concentrations had increased substantially, matching the levels detected at Enceladus. The implications extend beyond just having the right ingredients. High phosphorus availability could accelerate the chemical reactions that lead to complex organic molecules. It could make energy storage more efficient. It could enable the formation of more stable molecular structures. In a hypothetical Enceladus biochemistry, abundant phosphorus might be an unexpected advantage rather than a limiting factor. Meanwhile, other discoveries kept accumulating. Scientists analyzing archived Cassini data with improved techniques continued finding new organic compounds. In 2026, researchers announced the detection of additional molecular families including aliphatic esters, heterocyclic compounds, and nitrogen-bearing organics. Each new compound class expanded the known chemical diversity of the ocean. These weren't simple molecules. Some contained 15 or more carbon atoms, complex enough to hint at interesting chemistry occurring beneath the ice. The variety suggested that whatever processes were producing these compounds weren't following a single narrow pathway but were generating diverse molecular structures through multiple chemical routes. One particularly significant finding involved molecules that appeared fresh, meaning they had been ejected from the ocean just minutes before Cassini sampled them. This distinction mattered because of an ongoing debate about where the organics were actually forming. Saturn's magnetosphere bathes Enceladus in intense radiation. High-energy particles constantly bombard the Moon's surface and the ice grains floating in the E-ring. This radiation can drive chemical reactions, potentially creating organic molecules from simpler starting materials through purely physical processes that have nothing to do with ocean chemistry or biology. Some researchers argued that radiation synthesis could explain at least some of the organics detected in the plumes. Laboratory experiments showed that when ice containing simple compounds like methane and carbon dioxide gets exposed to radiation similar to Saturn's environment, complex organic molecules form on the ice surface. This raised a troubling possibility. Were scientists analyzing ocean chemistry or just radiation-generated artifacts? The fresh grain analysis helped resolve this question. Grains that had been in space for years might indeed have radiation-generated organics coating their surfaces. But grains ejected minutes before being sampled wouldn't have had time for significant radiation processing. The fact that these fresh grains still contained complex organics meant that at least some of the compounds definitively originated in the ocean rather than forming in space. This confirmation strengthened the case that Enceladus's ocean hosts active organic chemistry driven by processes occurring in the water itself, likely involving the interaction of dissolved compounds with minerals and heat at the ocean floor. Which brings us back to the fundamental question. Does having all the right ingredients mean life actually exists there? Scientists approach this carefully. The presence of water, energy sources, and organic molecules creates conditions where life could potentially exist. It doesn't prove life is actually there. Earth's hydrothermal vents demonstrate that these conditions can support life, but that observation doesn't automatically transfer to another world with different history, different chemistry, and different environmental constraints. Consider the methane detected in Enceladus's plumes. On Earth, methane in hydrothermal environments often comes from microorganisms called methanogens. These organisms consume hydrogen and carbon dioxide, using the chemical energy from that reaction to power their metabolism, and they release methane as waste. The process is called methanogenesis, and it's one of the oldest metabolic strategies on our planet, possibly dating back to some of the earliest life forms. Enceladus has hydrogen, carbon dioxide, and methane. Mathematical models show that the observed methane levels are consistent with biological methanogenesis. But they're also consistent with purely geological processes. Certain types of water-rock reactions can produce methane without any biology involved. The methane alone doesn't tell us which process is responsible. This ambiguity frustrates researchers because it represents exactly the kind of measurement that could go either way. You can construct a perfectly reasonable scenario where microbes in Enceladus's ocean are producing methane through metabolism. You can also construct an equally reasonable scenario where geological chemistry alone explains everything observed. Both scenarios fit the available data. What scientists really need is a biosignature, a measurement that can't be easily explained by non-biological processes. On Earth, certain molecular patterns serve this purpose. Life tends to favor specific isotopes of carbon. Living organisms produce molecules with particular chirality, meaning they're asymmetric in consistent ways. Cellular structures have distinctive sizes and shapes. Complex organic molecules in living systems follow patterns that random chemistry typically doesn't produce. Detecting any of these signatures at Enceladus would shift the conversation dramatically. But Cassini wasn't designed to make those measurements. Its instruments could detect what molecules were present and estimate their abundances, but they couldn't perform the detailed analysis needed to distinguish biological from non-biological origins for most compounds. That limitation shapes how we interpret everything Cassini discovered. The mission revealed an ocean that appears habitable by every criterion scientists can currently evaluate. It found chemistry that could support life. It detected energy sources that life could exploit. But it didn't, and couldn't, directly detect life itself. Which means the story of Enceladus has reached a critical juncture. We know enough to recognize this moon as one of the most promising places in the solar system to search for life beyond Earth. We don't know enough to say whether that search would actually find anything. That gap between what we've learned and what we need to know drives the current scientific conversation. Return to Enceladus. But not with instruments designed for general planetary exploration. With technology specifically built to detect life, or at minimum, to distinguish between biological and non-biological chemistry with far greater precision than Cassini managed. The engineering challenges are significant. Enceladus orbits Saturn at an average distance of about 238,000 kilometers. Getting there requires navigating the complex gravitational environment of the Saturn system, timing flybys with extreme precision, and managing fuel budgets that limit how many close approaches a spacecraft can make. Cassini completed 23 targeted flybys of Enceladus during its mission. Each flyby provided only seconds to minutes of close-range data collection as the spacecraft screamed past at several kilometers per second. A dedicated mission would need to do better. Some concepts propose entering orbit around Enceladus itself, though the Moon's low gravity makes orbital insertion difficult without substantial fuel. Others suggest multiple flybys from Saturn orbit, optimized to pass directly through the densest parts of the plume where material concentration is highest. The most ambitious concepts discuss landing on the surface near the Tiger Stripe fractures, deploying instruments that could analyze fresh ice as it falls from the sky, or even melting through the ice shell to access the ocean directly. That last option sounds like science fiction, but it's being seriously discussed. A cryobot, a probe designed to melt through ice using heat, could theoretically penetrate Enceladus's shell. The ice is estimated to be 20 to 25 kilometers thick in most places. For perspective, the deepest hole humans have drilled on Earth reaches about 12 kilometers, and that took decades of work on solid ground with massive equipment. Doing the same thing on a distant moon with a robotic probe presents extraordinary technical obstacles. Even if you solve the penetration problem, you face others. How do you maintain communication through kilometers of ice? How do you power the probe for the months or years needed to melt through? How do you prevent contamination of the ocean with Earth microbes that might hitch a ride on the spacecraft? And perhaps most critically, how do you ensure the probe can actually function in the high-pressure, dark, potentially chemically hostile environment it would encounter beneath the ice? These aren't rhetorical questions. They represent active areas of research and engineering development. NASA and other space agencies have funded studies examining each of these problems. Some solutions exist. Others remain theoretical. The technology to land on Enceladus and collect samples exists right now. The technology to penetrate the ice and reach the ocean does not, at least not in a form ready for deployment on an interplanetary mission. Which brings the conversation back to the Plumes. They solve the access problem. You don't need to land, don't need to drill, don't need to navigate through kilometers of ice. The ocean comes to you, erupting into space at 200 kilograms per second. Fly through it. Collect samples. Analyze them in real time as your spacecraft passes through the plume, or gather material to return to Earth for study in laboratories with instruments far more sophisticated than anything that fits on a spacecraft. Sample return missions have been done before. Japan's Hayabusa missions returned material from asteroids. NASA's Stardust mission collected samples from a comet. But those were solid particles from airless bodies. Returning ice grains that contain dissolved organic molecules and potentially biological material presents different challenges. The samples need to remain frozen during the entire journey back to Earth, which could take years. They need to be protected from radiation that could alter their chemistry. And they need to be handled in ways that prevent any possible contamination from affecting Earth's environment. That last concern isn't paranoia. It reflects a real principle in planetary protection. We don't know what might exist in Enceladus's ocean. The probability that it poses any threat to Earth's biosphere is essentially zero, but essentially zero isn't the same as absolutely zero when you're talking about bringing extraterrestrial material to a planet with complex interconnected ecosystems. Any sample return mission would require containment protocols, quarantine procedures, and analysis methods that ensure whatever comes back stays contained until we know exactly what it is. The alternative is in situ analysis. Instead of bringing samples to Earth, you bring the laboratory to Enceladus. Design instruments capable of detecting biosignatures in the plume material and mount them on a spacecraft that makes repeated passes through the erupting jets. This approach has advantages. No sample return means no contamination risk. No years-long journey back to Earth means faster results. And you can analyze far more material by flying through the plume multiple times than you could ever collect and bring home. But in situ analysis has limitations. Laboratory instruments on Earth are room-sized machines that consume substantial power and require human operators. Spacecraft instruments must be compact, lightweight, radiation-hardened, and fully automated. They can't do everything a terrestrial lab can do. The question becomes whether they can do enough to answer the fundamental questions about Enceladus's habitability and potential biology. Recent advances suggest they might. Fabian Klenner at the University of Washington and colleagues demonstrated that modern mass spectrometers, if optimized for the task, could detect individual bacterial cells in ice grains even if those cells made up only a tiny fraction of the grain's mass. The instrument wouldn't see the cell directly but would detect the specific molecular signatures that cellular material produces when vaporized and ionized in the mass spectrometer. This matters because it sets a detection threshold. If life exists in Enceladus's ocean at concentrations similar to Earth's oceans, and if plume material contains a representative sample of what's in the water below, then a spacecraft equipped with a sufficiently sensitive mass spectrometer flying through the plume should be able to detect it. Not with absolute certainty on a single pass, but with increasingly strong evidence as measurements accumulate over multiple flybys. The key phrase there is, if plume material contains a representative sample. Do the plumes actually carry cells if they exist? Or would any life in the ocean remain in the water while only non-living chemistry makes it into the jets? This question matters enormously for mission design. Laboratory experiments have shown that when water erupts through narrow channels under pressure, it can carry microorganisms along with it. Bubbles rising through water can scavenge cells from the surrounding liquid. But laboratory conditions don't perfectly replicate what happens in Enceladus's subsurface. The plume material travels through the ice shell, likely through networks of fractures and channels. Does that journey filter out larger particles like cells while allowing smaller molecules to pass? Or do the dynamics of the eruption carry everything along regardless of size? Scientists don't have definitive answers yet. The question remains open, studied through modeling, laboratory experiments, and careful analysis of what Cassini detected. What we do know is that the plume contains complex organic molecules, some with masses large enough that they could be fragments of cellular material. The presence of these molecules at minimum proves that relatively large organic structures can survive the journey from ocean to space. Whether intact cells could do the same remains uncertain, but it's not obviously impossible. This uncertainty influences how missions are designed. A spacecraft that assumes cells will be present designs its instruments one way, optimizing for detecting cellular biosignatures. A spacecraft that assumes only molecular fragments will be present designs differently, focusing on identifying chemical patterns that suggest biological processes even without intact organisms. The ideal approach probably involves instruments capable of handling both scenarios. Beyond the technical challenges, there's the timeline problem. Cassini ended in 2017. Any new mission to Enceladus would require years of planning, development, testing, and funding before launch. Then several more years of travel time to reach Saturn. We're looking at a minimum of 15 to 20 years between now and when a dedicated mission could begin returning data, and that's if everything proceeds without delays, which space missions rarely do. 20 years feels like an eternity when you're talking about a question this profound. But it's actually remarkably fast by the standards of planetary exploration. The gap between Viking's search for life on Mars and the Curiosity rover that followed up on those questions was 35 years. The gap between Voyager's first glimpse of Enceladus's smooth surface and Cassini's discovery of the plumes was 24 years. Science at this scale operates on generational timescales. which raises an interesting question about how knowledge accumulates. The scientists who will analyze data from the next Enceladus mission are probably in graduate school right now, or maybe even younger. They'll build on work done by the current generation of researchers, who built on discoveries made by the generation before them. Understanding Enceladus isn't just about building better instruments. It's about constructing a framework of knowledge that each generation adds to. That framework exists now, built across decades by thousands of researchers analyzing data, publishing papers, debating interpretations. But there's something peculiar about where we stand at this moment. For the first time, we have enough information to ask genuinely specific questions about a potentially habitable environment beyond Earth, but not quite enough to answer them definitively. It's like having assembled most of a puzzle only to discover the final pieces are locked in a box that won't open for another 20 years. Consider what we learned about the pH of Enceladus's ocean. Early models suggested the water was quite alkaline, with pH values around 11 to 12, similar to soda lakes on Earth. More recent refinements brought those estimates down to a range between 7.95 and 9.05, much closer to Earth's ocean conditions. That difference matters enormously for thinking about what kinds of organisms could survive there. At pH 12, you're looking at extremophiles adapted to highly caustic environments. At pH 8, you're in territory where many more Earth organisms could theoretically function. The revision didn't come from new data, but from better modeling of how Enceladus's ocean chemistry works. These models simulate water-rock interactions at the seafloor, track how dissolved gases equilibrate, account for temperature gradients within the ocean. They're sophisticated pieces of work, but they're still models, approximations based on limited measurements. Small changes in assumptions produce different pH predictions. Scientists run multiple versions with different parameters, seeing which ones best match what Cassini observed. The fact that recent models converge on more moderate pH values is reassuring, suggesting the approaches are maturing. But until an actual probe measures the ocean directly, uncertainty remains. The same pattern plays out across every aspect of Enceladus chemistry. Take phosphorus, the last of the essential CHNOPS elements to be confirmed. When scientists announced its detection in 2023, analyzing data Cassini collected years earlier, it wasn't just that they found phosphorus. They found concentrations at least 100 times higher than Earth's oceans, possibly several hundred times higher. That's not what anyone expected. Why would a small moon orbiting Saturn have vastly more phosphorus availability than Earth's enormous oceans? The answer likely relates to how water interacts with rock on Enceladus's seafloor. On Earth, phosphorus gets locked up in minerals that don't dissolve easily in seawater. It's a limiting nutrient, often the factor that constrains how much biological activity an ocean region can support. Enceladus apparently has geological conditions that keep phosphorus in solution, making it abundantly available. If life exists there, it's not phosphorus limited the way Earth's ocean ecosystems often are. But here's where interpretation gets tricky. Does abundant phosphorus make life more likely, because organisms have access to this critical element? Or does it suggest something about Enceladus's chemistry that makes life less likely through some mechanism we haven't considered? The straightforward reading says more phosphorus equals better conditions for life. Yet science has taught us repeatedly that straightforward readings can mislead when you're dealing with alien environments operating under different rules. The methane question illustrates this tension perfectly. Cassini detected methane in the plumes, which could be produced by biological methanogenesis, the process where certain microorganisms consume hydrogen and carbon dioxide and release methane as waste. Earth's deep sea vents host methanogens that do exactly this. The hydrogen Cassini detected could fuel such organisms. The carbon dioxide is present. The chemical environment seems compatible. Mathematical models confirm that biological methanogenesis could produce the methane levels observed without contradicting any other measurements. So we have a hypothesis that life exists on Enceladus, producing methane through a metabolism we know works on Earth, using energy sources and raw materials that Cassini confirmed are available. The hypothesis fits the data. Except there's an equally valid hypothesis that says the methane comes from purely geological processes, chemical reactions between water and rock at hydrothermal vents that produce methane without any biology involved. This hypothesis also fits the data perfectly. Two completely different explanations, one involving life and one not, both consistent with everything we've measured. That's the maddening reality of trying to detect life from 1 billion kilometers away using instruments that weren't specifically designed for that purpose. Cassini was built to study Saturn and its moons generally, not to search for biosignatures on Enceladus specifically, because nobody knew Enceladus had an ocean when Cassini was designed. The instruments performed brilliantly beyond their original specifications, but they have limits. The mass spectrometer that analyzed plume composition could identify molecules by their mass, but molecules with the same mass can have different structures, different origins, different implications. Distinguishing between them requires more sophisticated analysis than Cassini could provide. This is why the radiation debate matters so much. When some researchers proposed that radiation from Saturn's magnetosphere could produce organic molecules on Enceladus's surface, it wasn't an attempt to dismiss the possibility of life. It was scientists doing what they're supposed to do, proposing alternative explanations and testing whether they hold up. Laboratory experiments showed that yes, radiation can produce some organic molecules from simpler starting materials. The question became whether the organics Cassini detected could all be explained this way, or whether some required ocean chemistry to form. The resolution came from analyzing fresh plume material versus aged particles in Saturn's E-ring. The E-ring consists of ice grains ejected from Enceladus over time, some potentially hundreds of years old, exposed to radiation throughout that period. Cassini sampled both fresh plume material, seconds to minutes old, and ancient ring particles. When researchers found complex organics in the fresh material, organics that couldn't have spent long periods being processed by radiation, it demonstrated that at least some of these molecules originate from the ocean itself, not from radiation chemistry on the surface. That finding matters because it means Enceladus's ocean is actively producing complex organic chemistry, not just hosting simple molecules. The compounds detected include nitrogen-bearing and oxygen-bearing molecules, heterocyclic structures, molecules with 15 or more carbon atoms. These aren't the simple building blocks you might expect from basic chemistry. They're the kinds of molecules that in Earth's oceans participate in chains of reactions leading to even more complex chemistry. Laboratory simulations of Enceladus conditions support this interpretation. When researchers recreate the moon's ocean chemistry in high-pressure reactors, simulating the heating and freezing cycles that occur as water circulates between the warm seafloor and the cold ice shell above, they find that complex organics form readily. The minerals present on Enceladus's rocky core, interacting with alkaline water under these conditions, catalyze reactions that produce organic compounds without requiring any biological input. Which brings us to a subtle but important point about habitability. When scientists say Enceladus is habitable, they don't mean life definitely exists there. They mean the environment has the characteristics necessary to support life if life arose or arrived there somehow. Habitability is about potential, not confirmation. An environment can be habitable and lifeless. Earth was habitable for some time before life actually appeared, though we don't know exactly how long because the geological record doesn't extend back far enough. The three pillars of habitability are liquid water, energy sources, and organic chemistry. Enceladus demonstrably has all three. The ocean is global, at least 26 kilometers deep, possibly 31 kilometers, containing more water than some of Earth's smaller seas. The energy comes from tidal heating, Saturn's gravity kneading Enceladus as it orbits, generating warmth that keeps the ocean liquid despite surface temperatures of -198 degrees Celsius. The organic chemistry exists in the form of compounds Cassini detected, plus the complex molecules laboratory simulations show can form under Enceladus conditions. But there's a fourth factor that doesn't fit neatly into the traditional three-pillar framework: time. Has the ocean existed long enough for life to develop? The discovery of heat flow at Enceladus's North Pole, not just the active South Pole, suggests yes. That balanced heat production and heat loss indicates the ocean could remain stable for billions of years. Tidal heating isn't a temporary phenomenon but an ongoing process as long as Enceladus maintains its current orbit. The ocean is likely as old as the Moon itself, potentially dating back more than 4 billion years. 4 billion years is longer than life has existed on Earth. If time alone were sufficient, Enceladus has had plenty. But time isn't sufficient by itself. Life requires specific conditions during that time, and we don't know enough about Enceladus's history to say whether those conditions have been met. The ocean might have frozen and thawed repeatedly in the distant past. The chemistry might have been very different early on. Asteroid impacts could have sterilized the ocean periodically. Or none of those things happened, and the ocean has been a stable, chemistry-rich environment for billions of years, giving any potential life ample opportunity to establish itself. The honest answer is we don't know, and we won't know until we go back with instruments designed specifically to investigate these questions. That's the current state of Enceladus research, rich with tantalizing clues, frustratingly short on definitive answers, and absolutely demanding follow-up exploration. The instruments we need to answer those questions already exist. They're sitting in laboratories right now, tested and ready. Some are even flight-proven, having already demonstrated their capabilities on other missions. The technology isn't the bottleneck. The challenge is getting those instruments back to Enceladus. Several mission concepts have been proposed, each with different approaches to the same fundamental goal: sample the plumes directly and analyze them with instruments far more sophisticated than Cassini carried. Cassini was designed in the 1980s and launched in 1997. Its instruments, while revolutionary for their time, were built with 3-decade-old technology. A modern mission could carry mass spectrometers 1,000 times more sensitive, capable of detecting organic molecules at concentrations Cassini would have missed entirely. One concept called Enceladus Life Finder would fly through the plumes repeatedly, collecting samples and analyzing them with advanced mass spectrometry. The spacecraft wouldn't need to land or orbit. It would make multiple high-speed passes through the densest parts of the plumes, each time gathering fresh material directly from the ocean below. The beauty of this approach is its simplicity. No complex sample collection mechanisms, no drilling through kilometers of ice, no rovers or landers. Just fly through the plumes and see what's there. Another proposal takes this idea further. Instead of just analyzing samples in flight, a spacecraft could actually collect plume material and return it to Earth. Imagine having ice grains from Enceladus's ocean in terrestrial laboratories, where scientists could subject them to every analytical technique we possess. No need to miniaturize instruments or limit ourselves to what fits on a spacecraft. Every university lab, every research facility could examine the samples using methods we can't even deploy in space. The technical challenges of sample return are substantial but not insurmountable. The spacecraft would need to rendezvous with the plumes, collect material in specially designed cryogenic containers that keep the samples frozen at Enceladus temperatures, then make the journey back to Earth without contaminating or degrading what it carries. Round-trip time to Saturn is measured in years, more than a decade for most trajectories. But we've done harder things. We've returned samples from asteroids, from comets, even from the solar wind itself. What makes Enceladus uniquely accessible is that it hands us samples for free. We don't need to dig or drill. We don't need to develop exotic chemistry sets that work at -200 degrees Celsius. The ocean is literally erupting into space at 200 kilograms per second, and we just need to be there to catch it. Here's what modern mass spectrometry could detect. If microbial cells are present in the plumes, even a single cell within an ice grain would produce a distinctive signature. Cells have specific combinations of molecules, lipids forming membranes, proteins with characteristic amino acid sequences, nucleic acids with their sugar phosphate backbones. These combinations don't occur randomly in non-biological chemistry. A sufficiently sensitive mass spectrometer examining a sample containing even one cell would see patterns that scream biological origin. This isn't speculation. Researchers have modeled exactly what signatures different types of microorganisms would produce if they were present in Enceladus ice grains. They've calculated the mass spectrometry peaks, the molecular fragments, the isotope ratios. They've tested these predictions using Earth microbes flash frozen in simulated plume conditions. The signatures are clear and unambiguous. If life exists in Enceladus's ocean and cells make it into the plumes, we would know. But there's a catch. We need cells, or at least large biological molecules, to reach the plumes intact. The journey from ocean floor to space is violent. Water accelerates through narrow cracks in the ice, experiencing tremendous pressure changes and temperature swings. Would cells survive that? Would they arrive at the surface intact enough to identify? Laboratory experiments suggest yes, at least sometimes. Researchers have subjected various microorganisms to rapid decompression, flash freezing, and ejection at high velocity, conditions approximating what plume material experiences. Many cells rupture, their contents spilling out. But some remain intact or at least preserve enough structure that their biological origin would be detectable. It only takes one. The debate about whether life could exist on Enceladus ultimately comes down to energy. Not the bulk tidal heating that keeps the ocean liquid, but the specific chemical energy available at the molecular level to power metabolism. Life as we know it runs on chemical disequilibrium, using reactions that release energy when moving toward equilibrium. On Earth, photosynthesis creates massive disequilibrium by splitting water and storing energy in organic molecules. Other organisms then harvest that stored energy. Enceladus has no sunlight penetrating to its ocean. Any life there would need to run on chemistry alone, the way deep-sea vent organisms do on Earth. Those organisms exploit the chemical disequilibrium created when hot, mineral-rich vent fluids mix with cold ocean water. Hydrogen sulfide from the vents reacts with oxygen in the water, releasing energy. Hydrogen gas from the vents can react with carbon dioxide, producing methane and releasing energy through methanogenesis. Cassini detected both hydrogen and methane in Enceladus's plumes. The hydrogen comes from serpentinization, the same water-rock reaction that occurs at Earth's hydrothermal vents. Hot water reacts with iron-rich minerals in the rocky core, producing hydrogen gas. That hydrogen then rises through the ocean, potentially providing energy for life forms that can use it. The methane is more ambiguous. It could be geological, produced by the same water-rock interactions that generate hydrogen. Or it could be biological, the waste product of methanogenic microorganisms consuming hydrogen and carbon dioxide. Mathematical models show both explanations fit the data. We can't distinguish them from Cassini measurements alone. This is where a return mission becomes crucial. The isotope ratios of carbon and methane molecules carry information about their formation pathway. Biological methanogenesis preferentially incorporates lighter carbon isotopes, carbon-12 over carbon-13 because the enzymes involved work slightly faster with lighter atoms. Geological processes show different isotope preferences. A high-precision mass spectrometer analyzing methane from the plumes could measure these ratios precisely enough to determine whether biology is involved. The same applies to other molecules. Amino acids, if present, could be left-handed or right-handed, mirror images of each other. Life on Earth uses exclusively left-handed amino acids. Finding that same preference in Enceladus samples would be powerful evidence for biology, because non-biological synthesis produces equal mixtures of both forms. These are the kinds of measurements that require either sample return or instruments much more capable than Cassini carried. Cost is the inevitable obstacle. A flagship mission to Enceladus, equipped with state-of-the-art instruments and possibly sample return capability, would run several $billion. That's a substantial fraction of NASA's planetary science budget for many years. Competing priorities include Mars sample return, missions to other ocean worlds like Europa, and continued exploration of the outer solar system. Enceladus is compelling, but it's not the only target worthy of investigation. Which raises an interesting strategic question: should we search for life where it's easiest to reach, or where it's most likely to exist? Europa, Jupiter's ice-covered moon, also has a subsurface ocean, potentially with more water than Enceladus. It's closer to Earth, requiring less travel time. But it doesn't have convenient plumes offering free samples. Reaching Europa's ocean would require landing on the surface and drilling through kilometers of ice, a vastly more complex undertaking than flying through Enceladus's plumes. The plumes make Enceladus the low-hanging fruit of ocean world exploration. We can characterize its ocean chemistry, search for biosignatures, and potentially detect life if it exists, all without ever touching the surface. That accessibility is compelling. If we're going to search for life beyond Earth, why not start where it's easiest? But accessibility cuts both ways. If Enceladus is easy for us to sample, it's also easy for contamination. Every spacecraft we send carries Earth microbes despite our best sterilization efforts. Those microbes, freeze-dried and dormant, could potentially survive the journey and, if they somehow reached Enceladus's ocean, might find it habitable. The plumes mean any contamination at the surface could potentially work its way down into the ocean through cracks in the ice. This is why planetary protection protocols exist. Before we send any mission to Enceladus, we need to ensure we're not contaminating the very environment we're trying to study. The spacecraft must be sterile to standards far exceeding normal spaceflight requirements. Every component, every instrument, every square centimeter of surface must be either sterilized or demonstrated incapable of reaching the ocean. It's technically achievable but adds complexity and cost. The irony is rich. We might discover life on Enceladus only to realize we can't study it up close without risking contamination. Or we might find an environment so extreme that Earth organisms couldn't survive there anyway, making contamination concerns moot. We won't know which until we go and look. The more we learn about Enceladus, the more questions emerge, each one deepening our understanding while revealing how much remains unknown. Beyond the practical challenges lies something more fundamental: what finding life on Enceladus would mean for us. Not just scientifically, but philosophically. We've spent our entire history assuming Earth is special, that life is rare, that we're alone in a vast, cold universe. Enceladus could shatter that assumption overnight. Consider what it would take for life to exist there. The ocean has been isolated from Earth's biosphere for the entire history of both worlds. If we found life in Enceladus's ocean, it couldn't have come from Earth. It would represent an independent origin of life, a second genesis. And if life arose twice in one solar system, the implications are staggering. The Drake equation attempts to estimate the number of communicable civilizations in our galaxy. One of its key variables is the probability of life arising on a suitable planet. We have exactly one data point for that variable, Earth. Finding life on Enceladus would give us a second data point, suggesting life isn't a cosmic fluke but something that emerges readily given the right conditions. Suddenly, the galaxy looks very different. But there's a darker possibility. What if we find life, and it's related to Earth life? What if panspermia, the transfer of life between worlds via meteorite impacts, has been happening in our solar system for billions of years? That would mean Enceladus life and Earth life share a common ancestor, making them not independent origins but branches of the same tree. Still fascinating, but not quite the same paradigm shift. We could distinguish between these scenarios through genetic analysis, assuming Enceladus life uses DNA or something analogous. If its genetic code is fundamentally different from Earth's, independent origin becomes highly probable. If it's similar, we'd need to explain why, either through panspermia or by arguing that certain molecular structures are so optimal that evolution inevitably converges on them. There's also the possibility we find an ocean full of organic chemistry, all the building blocks present, energy flowing through the system, but no life. That would be almost as significant as finding life, because it would tell us something crucial: having all the right ingredients isn't enough. Life requires something more, some additional factor or threshold we haven't identified. That knowledge would reshape how we search for life elsewhere. Time is another variable we haven't fully considered. Earth's life arose relatively quickly, within the first billion years of the planet's history. Enceladus's ocean might be billions of years old, given the heat balance data suggesting long-term stability. If life hasn't arisen there despite billions of years of favorable conditions, that tells us something about the probability of abiogenesis, the transition from non-living chemistry to living organisms. Maybe life requires larger volumes. Earth's oceans contain vastly more water than Enceladus's ocean. Perhaps abiogenesis is a numbers game, requiring countless molecular trials before the right combination emerges. A smaller ocean might simply not provide enough opportunities. Or maybe surface processes matter more than we think. Earth's early atmosphere, its day-night cycle, its tides driven by the moon, all might play roles we don't yet understand. These are the questions that keep astrobiologists awake at night. Not just, is there life on Enceladus, but what does the answer tell us about life everywhere? Every outcome teaches us something profound about our place in the universe. The technology curve is moving in our favor. The instruments we can build today are orders of magnitude more sensitive than Cassini's equipment. Mass spectrometers can now detect individual molecules, distinguishing between isotopes with precision Cassini couldn't approach. Sample collection systems can capture ice grains intact, preserving their chemistry for detailed analysis. We're approaching the capability to definitively answer the life question, not through inference or statistical analysis, but through direct detection. Several mission concepts exist in various stages of development. NASA's Enceladus Orbolander would orbit the Moon, repeatedly flying through the Plumes before eventually landing near the Tiger Stripes for surface analysis. The European Space Agency has proposed similar concepts. China has announced plans for outer solar system exploration that could include Enceladus. The question isn't whether we'll return, but when and under whose flag. Political will fluctuates with budget cycles and changing priorities. Right now, Mars sample return consumes much of NASA's planetary science budget. The James Webb Space Telescope, while revolutionary for astronomy, wasn't cheap. Every flagship mission competes for limited resources. Enceladus must wait its turn, demonstrating value against other worthy targets. But here's something worth considering. Enceladus might be the best shot we have at finding life in our lifetime. Mars is fascinating but dry and dead on the surface, with any potential life buried deep underground where we can't easily reach it. Europa is compelling but requires drilling through kilometers of ice. Titan is intriguing but so cold that its chemistry operates on timescales we barely understand. Enceladus literally spits its ocean into space, offering us free samples on every orbit. That accessibility is precious. The scientific return on investment could be extraordinary. One confirmed biosignature, one unambiguous detection of life, would justify the entire cost instantly. Even negative results would be valuable, constraining our models of habitability and abiogenesis. Either way, we learn something fundamental about the universe. There's also the inspiration factor, harder to quantify but no less real. The Apollo program inspired generations of scientists and engineers. The Hubble Space Telescope fundamentally changed how the public engages with astronomy. A mission to search for life on Enceladus could have similar cultural impact, especially if it succeeded. Imagine the moment when scientists announce they've detected definitive evidence of extraterrestrial life. The world would stop and pay attention. That moment might be closer than we think. Recent studies suggest that even current technology could detect a single bacterial cell if it were present in a plume ice grain. The mass spectrometers we're developing can identify not just what molecules are present, but their three-dimensional structure, their chirality, whether they show the kind of ordered complexity that only biology produces. We're not talking about ambiguous chemical signatures requiring years of debate. We're talking about detection methods that could provide clear, definitive answers. The challenge isn't capability anymore. It's commitment. Are we, as a civilization, willing to prioritize the search for life beyond Earth? Are we willing to invest the resources necessary to answer one of humanity's oldest questions? The technology exists. The target is waiting. All that's missing is the decision to go. Meanwhile, Enceladus orbits Saturn, indifferent to our debates and budget constraints. Its plumes continue erupting, carrying ocean water into space where it freezes and falls back as snow or escapes to form Saturn's E-ring. The chemistry in that ocean, whatever it is, continues operating according to physical laws that don't care whether we're watching. If life exists there, it's been living its alien existence for potentially billions of years, completely unaware that creatures on a distant blue world are arguing about whether to come looking for it. That's the part that gets to me. We might be this close to answering the biggest question in science, and the only thing stopping us is whether we choose to go. Not whether we can, but whether we will. The universe doesn't wait for us to make up our minds. It simply continues, indifferent and vast, while we debate and delay. Enceladus represents something more than scientific curiosity. It's a test of our priorities as a species. Are we explorers or not? Do we genuinely want to know whether we're alone, or are we content with speculation and uncertainty? The moon is there. The ocean is there. The plumes are there, offering us the easiest path to an alien ocean that we're likely to find anywhere in the solar system. Everything we need to know is within reach, suspended in ice grains floating through space, waiting for us to come and collect them. The only question remaining is whether we'll choose to reach out and take what's being offered. The answer will say more about us than it does about Enceladus. Looking back at everything we've learned, Enceladus went from an unremarkable frozen moon to potentially the most important scientific target in our solar system in less than 20 years. That transformation happened because we went there and looked. Not with preconceptions about what we'd find, but with instruments capable of detecting whatever existed. What those instruments revealed exceeded anyone's expectations. We found a global ocean beneath an ice shell. We found organic molecules, some complex enough to qualify as prebiotics. We found phosphorus at concentrations far exceeding Earth's oceans. We found energy sources that could power metabolism. We found chemistry that mirrors the conditions where life first emerged on our own planet. And we found all of this not by drilling through kilometers of ice or landing on a hostile surface, but by flying through plumes that deliver ocean samples directly to space. The evidence doesn't prove life exists on Enceladus. Science rarely deals in absolute proof, especially when studying environments we can't directly access. But the evidence demonstrates that Enceladus has everything necessary for life as we understand it. Whether that potential has been realized remains the fundamental unanswered question, the gap between what Cassini could measure and what we need to know. That gap is closable. The technology exists right now to detect biosignatures in plume material with enough sensitivity to identify individual cells if they're present. The mission concepts exist, detailed enough that engineers could begin building hardware tomorrow if funding materialized. The scientific questions are well defined, specific enough that we know exactly what measurements would answer them. Everything is ready except the decision to proceed. Which brings us to the uncomfortable truth about space exploration. The obstacles aren't primarily technical anymore. We can build the spacecraft, design the instruments, navigate to Enceladus, sample the plumes, and analyze what we find. The challenge is political and financial, convincing decision-makers that searching for alien life deserves priority over competing demands for limited resources. That's a harder problem than engineering, because it requires sustained commitment over decades. But here's what makes Enceladus special. It's not asking us to do something unprecedented. We've sent spacecraft to every planet in the solar system. We've landed rovers on Mars, orbited comets, returned samples from asteroids. A mission to Enceladus would use proven techniques, established methods, well-understood physics. The only new part is the question we're asking. Everything else is technology we've already demonstrated works. The potential payoff justifies the investment many times over. If we find life, even simple microbial life, it fundamentally changes our understanding of our place in the universe. If we find a habitable ocean with all the right chemistry but no life, that teaches us something equally profound about what conditions are necessary but not sufficient for biology. If we find evidence that the organic molecules come from radiation rather than ocean chemistry, that constrains our models of habitability. Every outcome advances our knowledge substantially. Consider the alternative. We could choose not to go, decide that other priorities matter more, let this opportunity pass while focusing resources elsewhere. That's a legitimate choice. Space exploration involves trade-offs, and reasonable people can disagree about what deserves funding. But we need to be honest about what we'd be giving up. We'd be consciously choosing to leave the most accessible potentially inhabited environment in our solar system unexplored, possibly for decades, because the timeframes for these missions are generational. The scientists who designed Cassini started their careers in the 1970s. The spacecraft launched in 1997 and didn't reach Saturn until 2004. It operated until 2017, spanning most of those scientists' working lives. A mission launching today wouldn't return data until the 2030s or 2040s. The researchers proposing these missions might not live to see the results. They're asking questions for future generations to answer, building frameworks of knowledge that will outlive them. That's how science at this scale works. But those future generations will inherit whatever decisions we make now. If we choose to explore Enceladus, they'll inherit the data, the discoveries, possibly the confirmation that life exists beyond Earth. If we choose to wait, they'll inherit the regret of knowing we had the capability to answer profound questions and simply didn't bother. That's the choice facing us, not whether we can go to Enceladus, but whether we value the answer enough to commit the resources necessary to get it. The ocean is there. The chemistry is there. The plumes are erupting right now, carrying samples we could analyze if we were present to collect them. Saturn's gravity continues kneading Enceladus, generating the heat that keeps that ocean liquid and potentially habitable. These processes operate on timescales measured in billions of years. They'll continue regardless of what we decide. The universe doesn't wait for human consensus. What happens next depends entirely on choices made by people who will never see Enceladus firsthand, who will never touch its ice or sample its ocean directly. They'll make decisions based on budget spreadsheets, political considerations, competing priorities, and occasionally, if we're fortunate, the recognition that some questions matter enough to pursue regardless of the obstacles. Whether we return to Enceladus in our lifetime depends on whether enough people in positions of authority believe that finding out whether we're alone in the universe justifies the cost. The remarkable thing is that we're even having this conversation. A century ago, the idea of searching for life on other worlds belonged to science fiction. 50 years ago, we had barely begun exploring our own solar system. Today, we're debating whether to send sophisticated instruments to a distant moon to search for microbes in an alien ocean. The pace of progress has been extraordinary. The next steps are within reach. Enceladus will still be there in 10 years, 20 years, however long it takes us to decide to return. The ocean will still be erupting into space. The chemistry will still be operating. The only variable is whether humans choose to go look. That decision will reveal as much about us as discovering life would reveal about the universe. Are we genuinely committed to exploration, or do we prefer the comfort of familiar questions over the challenge of finding actual answers? The plumes are waiting. The ocean is waiting. The biggest question in science has a potential answer floating in ice grains around Saturn, and all we need to do is go collect them. Whether we make that choice, and how quickly, will define how seriously this generation takes the search for life beyond Earth. The technology is ready. The target is accessible. The only thing missing is the will to act on what we already know is possible.